John, and in this talk, I'll walk you through a paper titled Automated Design of Agentic Systems by Shengran Hu, Cong Lu, Jeff Clune from University of British Columbia and the Vector Institute. This was published at ICLR 2025. At a high level, this paper asks a simple but powerful question. Instead of humans manually designing complex AI agents, can we get an AI system to design agents for us automatically? Okay, so I'll first explain what agentic system actually are, why manual design is hitting limits, and then introduce a framework called ADAS, automated automated design of agentic systems. After that, I'll show you how their meta agent search approach works, what benchmarks they evaluate on, and some interesting results and limitations. By the end of this talk, you should have a clear intuition for how an AI can write agent code and iteratively improve it, and why that might be an important next step for building more powerful systems. So to begin with, we have the problem manual agent design is limiting. Today, most agentic systems are still designed by hand. Researchers and engineers manually craft prompts, design workflows, decide how to call tools or APIs, and glue everything together with a custom code. This process is slow, expensive, and very domain specific. If you can change the task or model, you often have to redesign a lot of logic. We do have famous success stories like chain of thought prompting and self-reflection, but those are essentially individual tricks invented by humans. The space of possible agent design is huge, and we have explored only a small corner of it. So, historically, in machine learning, we have seen this pattern many times. Hand engineered features like HOG were replaced by learned CNN features. Manually designed network architecture gave way to neural architecture search, and then human design loss functions are now sometimes replaced by learned objectives. So the author basically asks, if everything else in machine learning has moved to manual design, to automated search and learning, why should agent design be any different? Why should we stick to human designs, right? So, so the key concepts, what are agentic systems? Before we get into automation, you need a shared understanding of what an agentic system is. You can think of agentic system as a workflow built around a foundation model. Instead of calling large language once, we wrap it in a multi-step process, which is like planning, reasoning, calling tools or APIs, and maybe like storing intermediate results in memory, and then reiterating until we get a final answer. But these systems are built from like building blocks like chain of thought prompting, external tool used, scratchpad memories, self-critique loops, or ensemble of multiple calls. Each building block is relatively simple, but can combine them in many ways, and that's where combinatorial complexity comes in. And once you have several blocks and you allow branching, loops, and condition, the number of possible agent design explodes. So there are countless ways to wire these components together, far more than human can reasonably explore manually. So that huge design space is exactly what ADAS tries to surge over automatically. So now introducing the design system, the author proposed ADAS, which is automated design of agentic system, as a new research direction. The goal is to automatically create powerful agent designs by searching over the huge space of possible workflows and discovering new building blocks along the way. So they organize ADAS into three classic components. The first is search space. This defines what kind of agent are even representable. If you restrict your space too much, you'll never discover interesting agents. The second is search algorithm. This is how you explore that space, how you propose new agents, how much you exploit what already works versus explore something novel, something new. And the third is evaluation function. This is how you score agents' accuracy on tasks, but also potentially cost, latency, or other objectives. So the key innovation is choosing the search space very ambitiously. They define agents directly as code written in a Turing complete language like Python. And in theory, that means the search space includes any agentic system you could implement in code, not just a fixed prompt template or a small routing graph. Now, our approach with meta agent search. To actually explore this huge code space, the authors introduced meta agent search. This idea is to have like a meta agent, which is basically a powerful LLM and whose job is not to solve the task directly, but to write agent code that will solve the task. So the process goes in four steps. First, we archive initialization. They start with a small archive of baseline agents, such as chain of thoughts or a self-refine. These are like initial stepping stone. Then it's like the generate new design. The meta agent looks at the archive and writes new Python code implementing a candidate agent, often by recombining or modifying existing ideas. And then the third step is test and refine. The candidate agent is run on validation tasks. The meta agent then self reflects on the errors and can revise the code up to a few times, like in engineer debugging. And the fourth step is update archive. If the new agent perform well enough and is sufficiently different, it gets added to the archive along with the performance metrics. So this loop repeats, and over time, the archive becomes a library of discovered agents. And the meta agent can use these as inspiration for even more sophisticated designs. Now, this is like architecture and key component, which is like even though the search space is very huge, the author keep each individual agent very simple and standardized. An agent is roughly 100 lines of Python code, and with a single forward function that takes in information and returns a response. That makes it easier for meta agent to reason in a consistent format. Under the hood, the meta agent itself uses strong models like GPT-4 to generate and edit this Python code. So you can think GPT-4 acting as an automated programmer writing new agent architecture. They also add, explicit mechanisms to encourage novelty, and the meta agent is just asked to reflect how a new design differs from existing archive. So it doesn't just keep rediscovering the patterns. Now, the experiments and the diverse evaluation domains. To test whether automatically design agents are actually useful, the author evaluate them on several different step domains. The first is ARC challenge, which is like grid pattern based learning challenge. The second one is like a math reasoning. MGSM is like a multilingual math problem requiring multiple step reasoning. And the third is a reading comprehension, where we drop data set, which is like required to understand and do numerical reasoning from text. And the fourth is graduate science, which is like the GPQ and MMLU testing for advanced scientific knowledge, and it is used across domains. So, importantly, these agents discovered by search are not tested on the same model they were created with. They are evaluated with GPT 3.5 and then checked for variability across other models like Claude and GPT-4. And across domains, this tells us like whether the discovered agent are genuinely robust or are just overfitting one setup. So this is like the key result. Um, the results are quite encouraging as well. Overall, the agents discovered by Meta Agent um, that search outperform a strong hand design baseline. So on Arc, it was like over 25 iteration. And other key factors finding was like robust transfer as well. And this suggests that the search is discovering general design patterns, not just one-off correct trick tuned to particular data set or model. Now, what are the limitations? The first one is like knowledge bottleneck. Performance gains smaller or challenging science question where foundation model knowledge is inefficient. So now if we try the same approach with the newer model, which is like GPT-5 and Claude Sonnet, um, and other models like Opus, Cloud Opus, we might get better results. So I think this thing is kind of taken care of. The single step task, which is like a current evaluation limited to QA task, future work should extend to complex multi-step environments with iterative and agent environment interaction. The third is like the experiment show real measurable success. The meta agent search consistently outperforms this. Yeah. So the key takeaway is like a paradigm shift from moving to from like manual agent design. We are moving to automated discovery through meta learning, and this can accelerate progress and unlock new architectures that human might not even conceive. Code as search space, using like Turing complete language like Python. This enables discovery of any possible agent design, prompts, workflow, tool use, and their combinations. And like the third is demonstrated success through the different task performed. So um, Meta agent search consistently outperforms state of art hand design agent with discovered solutions showing impressive transfer across domains and model. So exciting research horizon is like ADAS open pathways to high order meta learning and online continual learning post deployment as well, and understanding complexity emergence is both AI systems and human organization. All code is like open source in GitHub of Shengran Hu slash ADAS. And I'll stop here. Thank you for listening, and I'm happy to take um, any feedback in the comment. And a big shout out to the uh, folks who wrote this paper. This is a very interesting approach. I was just trying to understand and highlight and explain it in a much simpler terms to my audience. Thank you so much for watching. You have a good one.